In this part of the course, we'll look at a qualitative analytical technique called infrared spectroscopy. Now, by the end of the section on infrared spectroscopy, you should be able to explain all of the following. You should know what information infrared spectroscopy gives, know the three key regions of the infrared spectrum, you should know what causes bonds to vibrate at a given frequency and intensity. You should be able to interpret the infrared spectrum of small, simple molecules. You should be able to predict the vibrational frequency of functional groups in a molecule that you haven't seen before. And you should also know how to prepare a sample for infrared analysis and why calibration is important in the context of infrared spectroscopy. Now, spectroscopy in general concerns the interaction of electromagnetic radiation with atoms and molecules to give you some information about them. Now, we've seen this in the previous section about UV visible spectroscopy, where we looked at a form of spectroscopy which uses light in the UV and visible region. And what we saw is that you can use this technique to quantify the amount of material you have in a given solution, or to calculate the pKa of a functional group. Now we're going to focus on infrared spectroscopy, which uses light within the infrared spectrum. Now it turns out that light within the infrared region of the electromagnetic spectrum has enough energy in it to excite vibrational transitions in molecules. So when infrared light hits molecules, it causes those molecules to vibrate. Now the frequency or wavelength of light that you need to achieve each vibration is specific to each bond or functional group, which means you can use this technique to identify functional groups within molecules. However, what you can't use this technique for is complete structure determination. You can only tell if a molecule has a particular functional group. You can't tell how many of those functional groups it may have, or the structure of those groups within the molecule. Now the instrumentation, so an infrared spectrophotometer, is quite similar to a UV visible spectrophotometer. Now in the spectrophotometer you have a radiation source. Now this can either be something called a Nernst glower or a glow bar, or it could be an incandescent wire. If we're working in the near infrared region, so the region of infrared that is closest to visible light, we could be using a tungsten lamp. Now we start with the radiation source, and this radiation is split into two separate paths, just like in a double beam UV visible spectrophotometer. The radiation source can then pass through the sample and a reference simultaneously, and then the radiation arrives at a detector. This detector then outputs the absorption information from the infrared spectrum. So it tells you where the absorbances are within the spectrum. Now, just like with UV visible spectroscopy, this is a very quick and easy method to run. You can acquire a spectrum in several minutes, and this technique is also amenable to things like automation. Now, this is what an infrared spectrum looks like, and this is the infrared spectrum of hexane. So hexane contains carbon-carbon single bonds and carbon-hydrogen single bonds. And that's it. So on this spectrum, we have the carbon-hydrogen single bonds here, and we have the carbon-carbon single bonds much lower down in the spectrum. But this graph looks a bit unusual. So what's different about graphs from infrared spectroscopy compared to UV visible absorption spectroscopy? Well, firstly, the peaks are upside down. So in this spectrum, we have a scale of transmittance. So this is how much of the light is transmitted through the sample. So if we're at 100%, that means all of the light is transmitted through the sample, which means none of the light is absorbed. If we have 0% transmittance, this means that 100% of the light is absorbed. So actually in infrared spectrum, our peaks are upside down. So this is called a peak, even though it is going downwards in this graph rather than upwards. The x-axis has also been flipped, so the small numbers are actually on the right of the x-axis rather than the left. Now this has been plotted with wavelength increasing as you go to the right. Now for infrared spectroscopy we work in a unit called wave numbers, which is how many wavelengths you can fit into 1 centimetre. So as you move to the left of the spectrum, we can fit more wavelengths into 1 centimetre, which means that the wavelength is getting shorter. So high frequency, fast vibrations are found on the left-hand side of the spectrum, and as we go to the right, we're seeing lower frequency, slower vibrations. Here we have a molecule of nitrobenzene. I'd like to show you what happens to this molecule when it has different vibrational modes. So these vibrations are caused by infrared light at different energies. So here we have a static image of the molecule, and you can see that we have a benzene ring here with a nitro group attached. Now when we hit this molecule with infrared light with a frequency of 1500 wave numbers, this is the vibration that the molecule experiences. So what you can see here is that the vibration is mostly around the nitro group and around the nitrogen-oxygen bonds. Now if we change the energy of the infrared light, so we change it to a frequency of 3300 wave numbers, what we'll see instead is the vibration of the carbon-hydrogen single bonds in the ring. So each vibration gives you a different absorbance on the infrared spectrum, and it's this that you're using to determine which functional groups are present within the molecule. You've just seen a molecule vibrating when it's been hit by infrared light of different frequencies or different energies. But what's actually happening within that molecule, and why is it vibrating? Well, when you have atoms at either end of a bond and they're hit with infrared light, they may vibrate and they may move. Now this, of course, changes the positions of the atoms relative to each other. Now, different systems can have what are called dipoles. Now, a dipole, or dipole moment, is the product of charge and distance of separation between two atoms. So, for example, dipoles are commonly found when you have an electronegative atom, such as oxygen, bound to something that has a much lower electronegativity, such as hydrogen. Now, within that oxygen-hydrogen bond, the oxygen is able to pull the electrons in the bond closer to itself. And that sets up a dipole where you have a very slight negative charge on the oxygen and a slight positive charge on the hydrogen. Now, these dipoles, when you move the atoms relative to each other, this also changes the position of the dipole. So for example here, if we have a water molecule, let's say this is oxygen and this is hydrogen, these will have a dipole located between each oxygen and hydrogen bond. Now when we move the atoms relative to each other, this results in a change in the position of the dipole. Now we can see as we stretch one bond out and move the other bond to slightly shorter, it changes the position of that dipole. Now this change in position is what happens when energy, when correct energy, so given by light in the infrared region of the electromagnetic spectrum, hits the molecule. It causes it to vibrate. Now each type of bond or functional group will vibrate at a different but known energy. And that means that each functional group will give an absorbance in a different position on the infrared spectrum. And it's this that allows us to work out what functional groups are present within a particular molecule. So some vibrational modes are not infrared active and they don't absorb infrared light, and this is because there isn't a change in dipole. So if we look at the molecule at the top, this is the example from the previous slide, when we change the position of these atoms relative to this one, we will change the position of the dipole moment. And when we change the position of two atoms relative to each other, where the dipole is not perfectly in the center, we will still change the position of the dipole moment. But if we have two atoms with an equal electronegativity, the dipole is perfectly in the center of the bond between them. And so when we change the position, the dipole will not change position. What this means is that this vibration will not be caused by infrared light. So it's an infrared inactive vibration, whereas for these are called infrared active vibrations. So now if we move the positions of the atoms, what we can see is that the dipole positions have changed in the top molecules and in the top bonds, but in the one in the bottom, there is no change in the position of this dipole. So some vibrational modes are active and others are not active. And this is why we can only see certain functional groups in the infrared spectrum. Later, we will rationalize why different groups absorb at different points in the infrared spectrum. So we will look to understand why CH bonds, for example, absorb at around 3000 wave numbers, and why carbon-oxygen double bonds absorb at around 1700 wave numbers. And we'll also seek to understand why different groups have different intensities on the infrared spectrum. However, next we're going to look at the different functional groups and where they absorb, and go through the important areas that you should know about as students of pharmacy.